Now, let's apply the principle of equipartition of energy that we discussed earlier to study the energy of a gas system. We are going to study energy for gas system which are monoatomic gas system, diatomic gas system, and also polyatomic gas system. But again, I'm going to emphasize that for our discussion over here, we are not going to consider kinetic energy due to vibration. Those are not considered because they occur only at very high temperature, so we will not discuss it in our syllabus. So let's continue with monoatomic gas. Again, you have 3 ways to translate, 0 ways to rotate. The free degree of freedom is 3. So there are 5 different values that we are going to study for energy for this gas system. The first value that we're going to study is translational kinetic energy of a single gas molecule. So one gas molecule, how much translational kinetic energy does it have? So because it's translational kinetic energy, we are going to focus on kinetic energy contributed by translation. So translation, we see there's 3 different ways to move. Each different way will have a half kT of kinetic energy per molecule. So we know that for translational kinetic energy, it will be 3 times of half kT. That's why it will be 3/2 kT for translation kinetic energy of a monoatomic gas molecule. For the total translational kinetic energy, the word total here means by we are not only going to consider one gas molecule, we are going to consider all the gas molecules in the gas system. Because that involves all of the gas molecule, that means by your kinetic energy will now be adding a word total, and you are going to take the translational kinetic energy of one gas molecule multiplied by the total number of gas molecules that you have in the system. So from there you are able to get the total translational kinetic energy. So we are going to get this equation for translational kinetic energy of gas molecule. We are going to multiply it with the total number of gas molecules you have in the system. From there you are able to get the total translational kinetic energy. So multiply by big N, your equation will now be 3/2 nKT. But you can know from the ideal gas equation that this nKT over here is equal to PV and is equal to nRT, right? So you can translate into 3/2 PV using ideal gas equation. And you know the ideal gas equation also tells you that PV is equal to nRT. Okay, so there's 3 different ways to express the total translational kinetic energy of the gas system. Okay, moving on, we have average kinetic energy of a gas molecule. Now, average kinetic energy means by we are not going to restrict ourselves to discussion of translation. We are going to include all different ways that you can move. But as you can see, for monoatomic gas system, all the different ways you can move, all of them are actually translation, because there's no ways to rotate, there's no ways to vibrate. Okay, so because of that, the average kinetic energy of a gas molecule, represented by K with an average sign, which is a pointy bracket over here, is the same as the translational kinetic energy of a gas molecule. It's the same because there's no rotation involved, there's only translation. That's all the ways that you can move. So because you have only 3 different ways you can move, so that's why it's the same 3/2 kT. Again, it's coming back to the principle of equipartition of energy. Okay, then you have your total average kinetic energy. Total means by you are not going to study one gas molecule only, you are going to move on to the whole gas system, which involve all the gas molecules inside it. So again, you're going to take this K, add on the total under it, and again it's just taking the average kinetic energy of one gas molecule multiplied by the total number of gas molecules that you have. So now this equation will evolve to become 3/2 nKT, which can be changed to 3/2 PV and also 3/2 nRT using the ideal gas equation. Same idea as what we did for translational kinetic energy. Lastly, internal energy is a bit different from all these things that we discussed earlier. So we need to understand clearly what is internal energy first. So internal energy is energy internal to the system. So what kind of energy is internal to the gas system? Well, internal energy is represented by a symbol U, and it's the sum of kinetic energies and potential energies of all the gas molecules that constitutes a gas system. So inside your gas molecule, inside your gas system, there's a lot of gas molecules. All these gas molecules, they are moving around. So because of that, they have kinetic energies. And besides that, if the molecules happen to interact with other molecules, such as they attract each other or they repel each other, so the attraction and repulsion that we have here will contribute to the potential energy of the gas molecules also. So we are going to add up all the kinetic energy and all the potential energy, and the sum of all these kinetic energies and potential energies will be the internal energy. So if you represent it mathematically, this U, internal energy here, is taking the total kinetic energy of the gas system, adding it with the total potential energy of the gas system. Okay, that's the idea for internal energy. But we know from our discussion of the kinetic molecular model, which is a few videos earlier, we are going to study our gas system based on kinetic molecular model. And kinetic molecular model, we actually make an assumption that we are going to neglect all the intermolecular forces. That means, right, in between gas molecules, we are going to assume that there is no attraction or repulsion between these gas molecules. So we are not going to include a discussion of London dispersion. We are not going to include a discussion like hydrogen bond, metallic bond, or London dispersion, dipole-dipole forces. Those forces are neglected in our gas system based on the kinetic molecular model. So because of that, there's no attraction and repulsion. There will be no potential energy stored in between the gas molecules. In between the gas molecules, there's no interaction when they are apart. So there is no potential involved. So because there is no potential energy involved, the potential energies in between the gas molecules will be zero. That's why we are going to neglect potential energies when we are using the kinetic molecular model. So because of that, our internal energy has already been simplified. It dies down to become just the total average kinetic energy of the gas system. So what you see for internal energy here will be the same as the total average kinetic energy of the system. That's why U will have the same expression as K total. So this is the internal energy for monoatomic gas system. Again, it arises because we are studying the gas system using kinetic molecular model, which neglects IMF. Okay, if it neglects IMF, it makes the potential there's no interaction between gas molecules when they are apart anymore. There's no interaction between them anymore because they don't attract, they don't repel. So if there's no attract, there's no repel, we can think that in between these gas molecules, there's no longer potential energies. So potential energy is something like spring, right? So if you compress a spring or if you stretch a spring, then there's elastic potential energy. So same idea. If you have attraction or repulsion between them, if you bring them closer or you bring them apart, there will be potential energy involved. But now we are going to say there's no interaction between them. So that's why there's no potential energy. Okay, so that's monoatomic gas. Let's move on to diatomic gas. Diatomic gas, we are going to use the same slide, but we are going to do a bit of modification. Now you have rotation in the y-axis and rotation in the z-axis. Rotation in the x-axis, we say that there's no significant motion, so we are going to neglect any, there's no kinetic energy contributed by this rotation. So you see that the degree of freedom right now is 5, but for translational kinetic energy, we are only going to look at translation only. So because of translation only, there's only 3 different ways to translate. So that's why it's still 3 over 2 kT for translational kinetic energy and total translational kinetic energy. But for average kinetic energy, you are going to include all the different ways that you can move. And based on our discussion earlier, there's additional 2 different ways for molecules to rotate. So in total, there's 5 different ways to move. So the degree of freedom is 5. That's why you're going to take 5. And each degree of freedom has half kT of kinetic energy per molecule associated with it. So it's 5 times of half kT. So it's 5 over 2 kT for average kinetic energy. Again, we are not restricted to discuss translation anymore when we talk about average kinetic energy. So there's an additional 2 different ways to move. That's why your kinetic energy goes from 3 over 2 kT to 5 over 2 kT. It's because of the rotation. Okay, then you have a total average kinetic energy, which is just multiplying by the number of gas molecules in the system. So it's NKT, PV, and nRT, just like we said earlier. But again, it's 5 degrees of freedom. That's why it's 5 over 2 over here. Internal energy is the same as average kinetic energy because we are going to neglect potential energy. That's why it's the same expression as K total that we have here. So that's for diatomic gas. The translational kinetic energy doesn't change, but if you talk about average kinetic energy and also the internal energy, you need to include the 2 additional ways to move for rotation. Okay, that's the basic idea. For polyatomic gas, again, we are going to assume non-linear polyatomic gas for our discussion only. So it's 6 degrees of freedom. For translation, we are going to restrict to the 3 degrees of freedom that we have. So it's 3 over 2 always for translation. But for kinetic energy or total average kinetic energy, we are breaking down the restriction for translation only. We are going to include translation and rotation. So in total, there's 6 different ways to move. That's why it's 6 times of half kT, 6 over 2 kT. Multiplying by the number of gas molecules, you get the total average kinetic energy. So you have this expression over here, where you can translate, you can change between different expressions using ideal gas equation. And lastly, internal energy is just the same as total average kinetic energy due to we neglect intermolecular forces. So the expression will be the same as K total. Okay, I'm going through this very fast because basically the main idea is that translation, there's always three ways to move, so it's always restricted to 3/2 kT. Okay, but for kinetic energy or average kinetic energy, you are not restricted to translation anymore, you include rotation. So for monoatomic, there's no ways to rotate, so there's no additional energy. For diatomic, you have two additional ways to rotate, so it become 5/2 kT. For polyatomic gas, you have three additional ways to rotate, that's why you become 6/2 kT. Okay, one thing that I want to emphasize is always when the question asks about kinetic energy, look carefully whether they are asking for kinetic energy of one single molecule or they are asking for kinetic energy of the whole system. If they're asking it for the whole system, you have to multiply by big N to be changed into this equation, which can be translated into different expression based on the ideal gas equation. So always differentiate whether they are asking for kinetic energy of a single molecule or the whole gas system. And lastly, internal energy always refer to the whole system. You cannot have internal energy of a single gas molecule. That's just illogical because internal energy is energy internal to the gas system. So it always includes all the gas molecules in the system. So this internal energy always refers to the gas system and it never refers to one single gas molecule. Okay, so I hope you are able to differentiate clearly the translational kinetic energy of a gas molecule, total translational kinetic energy of gas system, average kinetic energy of gas molecule, total average kinetic energy of gas system, and also internal energy, and able to use the correct expression when they ask you to determine it. So that's it for the energy of gases. Thank you very much.